Today we're going to be talking about how to name alkenes and alkynes. In my previous video, we did alkanes. They're pretty easy. We're going to do alkenes, and specifically we're going to focus on when to use the numbers. So I mentioned it when I did the alkane video, and I said sometimes we're going to have to include numbers in the name when there's more than one variation. For an alkane, that doesn't really happen ever, except for when they're branch chain alkanes. In an alkene, that'll happen when the atoms get more than 4 carbons in length, or 4 carbons or more in length. You're going to need numbers. And I've got my model kits today, and I'm going to try to show you why we use numbers on some and why we don't use numbers on others. So let's start with drawing the structures. So the way I'm going to tell you to do these, the way I always start with them, is simple. Just do the carbons first. So this first one is 2 carbons, this next one is 3 carbons, and this final one is 4 carbons 3 times in a row, and there's a very specific reason I'm doing that. And note, if you notice, I don't have any double bonds in them. I'm just putting in single bonds between carbon. Now, the reason we're doing that is because we're going to add the double bond in after the fact. So, for this first one, there's only 2 carbons, so the double bond has to go there. So when we draw this, it's 2 C's, and then it has 2 H's. So you can put your H's like this, like in your table, in your reference table, if you think it's Q. Table Q has it like this, or you could put them like this. Ultimately, it doesn't matter, okay? Just keep in mind, if you drew them like this and like this would still count as a symmetrical molecule because we don't really worry about the position of the H's, because in 3 dimensions, they are in specific locations, and so that changes things a little bit. So there's my 2 carbons. The name, eth, ene, no number. Condensed formula, CH2, CH2. Now, this one's easy. Let's go to the next one, and we'll start running into some issues. Some people will do this, and so I'm going to choose to put the double bond here. Some people may look at this and say, well, they put the double bond. I'll use this as an example. There. So then if we draw the molecule out, right, it's going to look like this. There's 2 H's on this one. There's going to be 1 H there. And then this molecule is going to look like this. And again, whether you put the H, this middle carbon gets the H up or down, doesn't matter. In real life, it's free to rotate around, so it is rotating. So that doesn't really matter. And so you would then say, well, what about these? These look different. So here's what I want to show you. This represents the first one. So if you look at it, this is the double bond here. This is the single bond. The balls are the carbons. And now what I did was I got rid of all the H's just so we could focus on the carbons, because that's all we have to really worry about now. And then the other way that I drew it would be this one, okay? And so here's the second one, and that's that. And so if you look at them, here's what's really going on. They may look different, but in 3 dimensions, look at what happens. They're no different. They're the exact same molecule. All I'm doing is taking one molecule, here's another angle, and I'm just drawing it like this. I haven't actually changed the molecule, I just rotated it, okay? That would be like saying, you know, this pen is somehow different from this pen because the point's in the other direction. It's the same molecule, it's the same pen, and it's the same thing here. If I drew it like this, all I would do is just take my molecule and rotate it. I'll put it up here, and that's the same molecule. There it is, okay? And again, whether you drew this middle H up or down doesn't make a difference. It's free to rotate. Whether you drew these 2 H's on the right sideways in the bottom, or top and on the side, or on the angles, kind of like splitting the difference, it doesn't make a difference, because in real life they kind of move wherever they want to, and you don't really have control over that. So all we really care about when we're comparing molecules is how many carbons on this carbon, or how many H's on this carbon, how many H's on this one, how many H's on this one, and then the double bonds, how many of them there are and where are they. So these molecules are the same thing. So because of that, we're not going to change the name. This is just going to be propene. Done. It's that simple. Okay, there's no numbers, there's no variations. If you drew it this way or if you drew it this way, they would both be correct. Your condensed formulas would be different. Okay, this would be CH2, CH, CH3, and then this one would be but if you look, it's just the condensed formula backwards. It's CH2. Well, the start here is CH2. Well, this one is CH2, and then the middle one is CH in both cases, and then the far left and the far right are CH3. So it's just the reverse condensed formula, which is totally fine too, as long as it gets you the same molecule. Now, another question I get a lot is, well, if you were looking at the condensed formula, how would you know there's a double bond there? And the answer is, unfortunately, let's go to another page. The way you would figure that out is to uncondense it. So if you uncondense this, you'd say, okay, there's my first carbon, it has 2 H's. Then there's my second carbon, it has 1 H. Notice I didn't put a double bond in there because I don't know it's there. And then here's my third carbon, and it has 3 H's. And then you look at this and you say, hey, octet rule says all carbons want to have 4 bonds. This carbon has 4, 1, 2, 3, 4. But this carbon only has 3, and this carbon only has 3, so these 2 carbons are 1 bond short. Then you go back in and say, there must be a double bond there to make all the carbons have 4 bonds. So that's how you have to do it. You actually have to go in, find the area where you're missing a bond, and then put the double or triple bond in. So unfortunately, they don't spell it out for you. If you were given the name, it would be in the name. The ENE tells me there's a double bond there. And so that's one thing. But if you were just given the condensed and you had to draw the structure, you'd have to figure that out on your own. Now let's go to our favorite one, these guys. So there's 3 versions of butene. So these would all be called butene, and when you're doing these, the easiest way to do it is I like to start on the left, and I'm just going to put my double bond in there, and then move it 1 carbon over there, and then I move it 1 carbon over there. So now I've hit every version. All right, then we're going to number it. We're going to call this 1, 2, 3, 4 carbon 1, 2, 3, 4, and then this would be carbon 1, 2, 3, 4. And so if we name these, right, this is where we need a numbering system in the name, because we can't have all 3 of these be the exact same name. We need to differentiate between them. So I'm going to call this 1-butene because the double bond is between carbon 1 and 2. This would be called 2-butene. And if you thought this would be called 3-butene, you are wrong. It's actually 1-butene again. Okay, so I did this on intentional. The numbering is wrong. Okay, and here's the reason why. So here's my first butene. So it's 4 in a row. Double bond is between carbons 1 and 2. Put it right there. Here's my second butene. It's 4 in a row. The double bond is between carbons 2 and 3. And then here's my third butene. 4 in a row. The double bond is between carbons 3 and 4. So we thought. But I could just do this, and the first and the third are the exact same molecule. They're just backwards. So they're no different, which is why they don't get a different name. Whereas the middle one, no matter how I rotate it, right? No matter how I rotate this, the double bond is in the middle, and the double bond will never go on the ends just by physically manipulating the molecule. If I wanted to get the double bond at the end, I'd have to change the way the bonds are connected. Whereas with these two, all I have to do to make the double bond be on either end is just rotate the molecule. And if I rotate the molecule without disconnecting anything, well, that's not a different molecule. That doesn't count, okay? So that's all I have to do. I just have to rotate it, and now it's here. Rotate it again, and it's back to where it was. So what we would do, and this is what I'm trying to teach, is the numbering system. Here's the easiest way to do it. Since the double bond is closer to the right, I call this carbon 1, this carbon 2, this carbon 3, and that carbon 4. And then you can see there's 2 variations, all right? It's that simple. And so if there's more than 1 variation, you need to use a number to tell me where the double bond is. For ethene, it's too small. There's only 1 version, no number needed. For propene, it looks like there's 2 different versions, but you just flip it and it's the same molecule. When you get to 4 or more, now there are different versions, and the bigger you get, the more versions you have. So there's 1-butene, and then there's 2-butene. So a good way of figuring it out is this. If you were to draw a bunch of carbons in a row, so I'm just going to pick a random amount, 1, 2, 3, 4, 5, 6. if you were to put a line right through the middle of the molecule, then it turns out that's how many versions of the molecule there are. Meaning I could put the double bond here, here, and here, right in the middle, and I get 3 different versions of this molecule. If I put the double bond here, well, it's just the flipped version of this one. And if I put it here, it's just the flipped version of this one. So you can go through, once you get the double bond, you can rotate it from carbon to the next carbon to the next. Once you hit the middle, you've done every version possible. So in this case, the middle would be right in the middle of this bond. So I put it here and here, and I've done every version. This one is just a flipped version of that one. Hopefully that makes a little bit of sense. The condensed formula is going to be, well, let's put the H's on. And so our condensed versions are going to be CH2, CH, CH2, CH3, and then this one would be CH2, CH, CH, CH3, and this final one, there's a missing an H here, so it's going to be CH2. And then the way to double check is make sure every carbon has 4 bonds. So when you look at this one, you say, all right, carbon 4 has 1, 2, 3, 4 bonds, carbon 3, 4, carbon 2, 1, 2, 3, 4, carbon 1, 1, 2, 3, 4. So as long as every carbon has 4 bonds, you did it right. Last question on the bottom is how many bonds are in a molecule of propene? This one tends to throw people off. Again, anytime you do this, I always recommend drawing it. The common mistake is to say prop 3, 3 bonds. So if we look at it, propene looks like this. It has a double bond, which means it's going to not have as many hydrogen as an alkane. So a common mistake is to say, okay, C3H6. Well, if I add 6 and 3 together, I get 9. And then you say, well, there's 9 bonds in it. That might be right, might be wrong. The smart way to do it is to draw it and count it. So in this case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So you get lucky, it's 9 bonds. With an alkane, it won't necessarily work out to be that. You can't just do that. And with an alkene, I don't think it works out as well either. So be aware of that. Always draw those out. And that's it for the alkene video. I'm going to pick up with the alkyne in their own video.